So after making the adjustments, we got a second hardboard piece, and after checking fitment, nice. What's up guys, we're back to making parts to support a rotary swap in my BMW i8. It's been a little bit longer than I would have liked, but I've been collecting some major components and I haven't had enough parts to make a reasonably coherent video, so it's been a minute. It's also the middle of July, and in my garage or glorified shed, it's a bit toasty. Over the last couple of weeks, the major components have rolled in, not the smallest of which is this subframe, which is gonna allow me to wire and fire the motor out of the car before I even take the stock driveline out. Speaking of fire, I also have my transmission, which is a DQ500 out of an Audi RS3 that also happened to burn to the ground. This seems to become a recurring theme, and hopefully my build does not suffer the same fate as the donor cars. On top of that, I also have the standalone ECU that's going to control the 13B as well as some other auxiliary components. For that, I pivoted from my original plan and went with an ECU Masters EMU Pro 16. You might be familiar with them from their EMU Black. This is a newer, more advanced ECU that's gonna have all of the configurability, controllability, and flexibility that I need to control my hybrid setup. And much like my initial choice, the ECU Master will be able to control the DQ500 over CAN bus without any additional programming or headaches that I'm gonna have to deal with. I also had a lot of stuff coming in terms of the transmission adapter plate, the flywheel adapter, and a whole bunch of stuff that we're gonna get to in future videos. The main topic for today's video is gonna be the oil pan, and that's gonna be constructed out of laser cut stainless steel. Unless you've been living under a rock for the past 6 years or not following any automotive fabrication YouTube channels, then you probably know who SendCutSend is. I've been using them since 2018 when I built my Tesla-powered E30 BMW. At that time, they were only laser cutting parts, but now they have all sorts of additional services like bending, anodizing, powder coating, threading, tapping, countersinking. Naturally, they were my first choice when it came to the oil pan and some other sheet metal components for this build. All of the components for the pan are 304 stainless steel. The 1/4-inch stainless steel pan rail is going to lend some strength and rigidity to help prevent the 13B long block from rotating under torque. While the motor is fully studded, the more you can do to prevent any sort of movement, the better off you are. The rest of the pan is going to be a mix of bent and welded sheet metal pieces, as well as a thicker flange to incorporate an OEM BMW level and temperature sensor. This way, within the car, the factory oil level sensing and temperature will still function. That's enough about me rambling about all the parts that I bought, so let's go build an oil pan. So this part's going to start where most things on this channel do, and that's in Fusion 360. The base of the pan is a large slab of 1/4-inch 304 stainless steel. That's going to double as our pan rail and also a support girdle to prevent rotation on the long block. We're utilizing a stock Mazda RX-8 oil pickup tube, which we may need to end up creating a small spacer to get the distance from the pan bottom right, get rid of the rail, and we can see all the internal baffling. And what this is going to do is help with the oil control. And these are rubber trap doors that, as the oil sloshes toward the pickup tube, the door will flap open and allow the liquid to flow in that direction. And then when you change direction under cornering, braking, or acceleration, the oil will then slam the rubber flap shut and thus contain the oil where it's supposed to be for easy access of the pickup. We have a -8AN ORB plug that we're going to use as our oil drain fitting. One thing you want to make sure you do is sink that fitting down so that the threads are flush with the bottom of the pan. That way you can get all of the bits and nastiness out when you change your oil. And then over here we have a flange for the oil level sensor, which we did a 3D scan of the top side just to get the dimensions that we need for the mounting plate. The only thing I didn't like about the end result is that it hangs the connector off the side of the pan. So if anything comes up and smacks it from underneath the car, you could lose that sensor. However, we do have the under tray there, so it is somewhat protected. And then obviously we can see that we have nice easy access for draining the oil when we go to change it. The main body of the pan was done in the sheet metal tool environment. It's really important that whenever you're working with sheet metal, that all of the operations that you do are in the sheet metal environment. If you start mixing some of the other tools with it, it's going to crash and burn when you go to try to create a flat pattern to export this to your friendly laser cutter like SendCutSend. I'm not going to go into any great detail on how you use some of these sheet metal tools. If you want to get a good starter course on how to design with sheet metal tools and export them to a file that you can get manufactured, then check out the link to HP Academy in the description below, and you can get a discount code off that course. And they make some really high quality motorsport centric content, so definitely check them out if you want to get educated on these topics. So that's all the time that we're going to spend in Fusion for this episode. Let's break out the welder and start assembling this thing. If you've ever priced out laser cut parts, they're shockingly cheap, so much so that I've pretty much retired my bandsaw and drill press except for really specific needs. However, in the case of my pan rail, that was about a $250 chunk of stainless, so really want to be sure that I didn't screw that one up. And a good way of checking fitment is with hardboard. This was about $28, and I'm really glad that I bought it because the first go around didn't go so well. I designed the pan rail around the step file that I had for the 13B, and it's been really accurate for most things so far. I designed my turbo manifold, my intake manifold, everything's fit really well, and I've had no complaints. However, when I got to the pan rail, I don't know what happened, but most of the bolt holes were shifted by some degree, enough that it wouldn't fit. It wasn't just a simple matter of opening up the holes, they were pretty much in the wrong spot by a not small amount. So we did the obvious thing and broke out the 3D scanner, scanned the real deal motor, and then redesigned the pan to have the proper bolt pattern. So after making the adjustments, we got a second hardboard piece, and after checking fitment, nice. So at this point, we've successfully amassed all the components that we need to assemble our oil pan. We've got our 1/4" thick pan rail, the sheet metal itself, which we'll take a deeper look at in a second, our internal baffling, and our rubber trap doors. We're also incorporating a factory BMW oil level sensor in this pan. This is out of an N20 car. In order to sink this deep enough into the pan, we needed a small spacer. And traditionally what I would have done is cut this out of a little thin strip of stainless, tacked it in the corner, and then tap it around with a hammer as I go. Try to get to the final shape. And that works fine, but you end up with a really thin piece of metal that is really easy to put a lot of heat into. One of the things that really still impresses me on laser cutting is things like this, where you can have a part that is 2.2 millimeters thick in cut length, or cut width rather, but the material itself is just shy of 5 millimeters. You have a nice thick spacer that's going to be a little bit more tolerant to putting heat into it when you go to fit this all together. And of course, on the sheet metal, the way that we designed this, we are going to have to give it a little bit of a tune-up. You can see this needs to come forward a little bit, but due to the bend, we need to hit this area and this area with a grinding disc just to make it clear. The sheet metal itself is 80 thousandths thick, 304 stainless, and then we opted for smaller filler pieces that will go and weld in rather than having a bunch of relief cuts and bends. 8N ORB plug for oil drain, which fits in really tight. Give that a little bit of a tap. And as you see from the CAD, that was sunk down just enough to put the threads roughly in line with the bottom of the pan so we can get full drainage of the oil. As we can see this time, the holes actually line up. One thing to note, on the final iteration, I did put some small slots on the front cover bolts because I did not know what the final gasket thickness was going to be. So now this can accommodate anything from a nice, thick, beefy OEM gasket to a thin film of RTV. SendCutSend really impressed me on this particular part, where it's bent on 4 sides and there's almost zero corner-to-corner rock. Having made a lot of oil pans in a past life, I've dealt with some sheet metal that was less than ideal, and this is going to go a really long way in improving the flatness of the final product. So I think our approach on this is going to be to tack this into the bottom of the pan, because by design it's flush with the bottom, and that'll give our flange a nice parallel surface to seat with. Next, we're going to take a look at the baffle, which is going to use these rubber trap doors to keep the oil where it's supposed to be. I didn't know these existed until I saw the video by Superfast Matt, where he builds an oil pan for his Dodge Viper, so shout out to him. I assume in the grand automotive Venn diagram of YouTube viewership that some of you also follow Matt. If you don't, I suggest you do. It's a good follow. If you got his video where he made the oil pan for the Viper, the fact that I'm making mine out of stainless steel, you're probably sitting there saying, "Stop, don't come back." Just waiting to go to the comments and tell me where I've gone all wrong. However, I had either the good fortune or misfortune of spending some time in the custom shop at Moroso, where I had the opportunity to build some really cool oil pans for some big name race programs in drag racing and NASCAR. One of the materials of choice for NASCAR pans is stainless steel, so I've had plenty of opportunities to screw that up in the past, and I've refined it a bit so I somewhat know what I'm doing. My time there gave me a lot of insights on what you can and can't do with sheet metal bending, as well as a lot of things that you shouldn't do, but you go and do anyway. The latter tends to send the technical review guys at SendCutSend a little bit crazy. Usually when I order a bent part, it goes something like this. A few minutes after I send my order, I get an email saying, "Hey bro, we can't make all these bends. Oh, by the way, here's a link to all the technical guidelines that you obviously chose to ignore." Respond with, "Oh, sorry about that. Just bend it as far as you can. I'll deal with the rest." "Okay, your funeral. We'll send it anyway." Now bear in mind there are limitations to this and your failure rate may vary, but generally speaking, the guy running the press brake works the magic and I get the part that I designed. Now bear in mind that these bend limitations that they're talking about are driven by the CAM software. It shows a machine crash, and typically when I do this, I have a long leg that interferes with another bend, but in reality when they go to bend it on the press brake, that long leg will deflect and then bounce back to its original shape. That being said, those CAM errors address some really niche situations that I deal with, so definitely take the advice of their technical review folks to heart. They do a really good job of saving you from your design errors that are going to cause manufacturing problems. Most recently, when I submitted the files for my transmission adapter plate, I had some holes a little bit too close to the edge for 1/2" aluminum, so they did catch that, asked me to revise the file, and I had no problem doing so, and the final part was just as it should be. With the baffle, one of the things we're gonna have to do is clean up this edge, just hit it with a sanding disc. There's a little bit of metal deformation when it bends, and if you can see, I don't know if it's gonna pick up, but it protrudes a little bit past the edge here, which is gonna keep the rubber trap door from sealing as well as it could against the flat surface, so we're just gonna make that flush. And then these install real easily. After tacking the corners of the baffle to the bottom of the pan, we're going to use silicon bronze filler rod to finish weld it the rest of the way. The reason that we chose this is because it has a significantly lower melting temperature than the stainless filler. It's going to prevent burn through to the other side of the pan, as well as limit some of the pulling and distortion that might result otherwise. So we managed to get the baffle welded into the bottom of the pan, and we got to check to see how flat it is, which it is probably going to be a little bit tweaked now. Yep, so we got a little bit of a rock to it now. So what we're gonna do is find the high spot, down, give it a little persuasion, and that's gonna be pretty acceptable right there. That'll work. You're not gonna get it perfect, but that's much better than it was, and it's gonna put less stress into the final weldment. And next step is to tack this thing on the rail and finish this thing up. For anybody wondering about my welding setup, it is a Miller Synchrowave 250 with a manufacture date circa 1989. Before we finish weld this, we want to go and check for flatness again. That's looking pretty good. The next step we got to do is prep it for back purging. If you're not familiar with back purging, when you weld stainless, if the backside of the weld puddle is exposed to the atmosphere, it will create a gray crusty surface. The technical term for gray and crusty is carbide precipitation. The way that we deal with that is filling the backside with argon. And so what we're going to do is seal off the base of the pan. We're going to affix a hose to the pan, which is going to feed argon through a second flow meter off my tank. That's going to purge the oxygen out and allow us to have a nice clean weld on both the inside and the outside. So I sealed off the back with some polyamide high temperature tape. If some of it melts around the edge where the weld is, it's not going to be a big deal. We just scrape it off with a razor blade. And the reason that we did this is to contain the argon within the pan. Argon is heavier than air, and with a bunch of open spaces on this block, the argon is just going to get wasted and end up on the floor rather than shielding the backside of the pan. We're going to get our pan into place. We're going to weld it on the block itself to act as a heat sink to keep everything flat. If you're going to weld any sort of oil pan, you need to do this on a block or something like a nice 1-inch thick piece of aluminum to act as a heat sink and retain the flatness. Otherwise, you're going to create a forbidden potato chip and nobody's going to have a good time. We're going to get the pan bolted down. I'm going to seal the oil level sensor area off with a piece of crumpled up aluminum foil because that's going to be way more heat than the polyamide tape can handle. And then we're going to get the back purge set up and finish this thing for good. You'll notice that some of the bolts are close to where we got to weld, so we're going to go as much as we can and then individually remove the fastener, stitch weld the area, then put it back, and then we're going to let this thing fully cool before we attempt to remove it. If you take the pan off while it's still warm, it's going to increase the chances of it still moving around. It's been about an hour. This thing's cool enough to take off the block. We can see what we ended up with. In terms of possible warpage, this part of the rail may have sucked in a little bit. This was the thinnest part and we put a lot of heat in for the flange right here. Other than that, some of the edges may have curled up just a little bit, and both of those we can fix with the orange persuasion tool. Ultimately, I think we might be okay though, so we'll find out. As far as corner to corner rock, we're actually in really good shape. I'm very happy with that. All of our polyamide tape survived. So measuring around, we're flat within about 0.03 of an inch for the bulk of the pan. We double that to around 6 in the corners, just out on the edge. But if we go behind the bolt holes across the ceiling area, that still meets the 0.03 flatness on the rest of it. So I'm really not going to do anything with this from here. Because these corners are lifted slightly by about 0.03 of an inch, once they're cinched down, all it's going to do is create a greater clamp force for where the pan actually has to seal. So that's not going to hurt us in any way. Last thing we got to do is install our rubber trap doors. And I'll take a little bit of lube so they slide in easier. I do like using petroleum jelly for any of this stuff because it cleans up really easily, it burns off easily, just dissolves in the oil, and it doesn't leave a thick, nasty residue like if you're using just normal synthetic grease. So, after a short ride on the struggle bus, we are done. As usual, if you made it this far, thanks for watching. This video actually should have come out ahead of the last one, but I forgot to order all the parts for my oil pan in time, so here we are. Stay tuned for the next episodes. We're gonna talk about stuff like my transmission and the adapter plate that's gonna make it to the 13B, some more control stuff, some more 3D printing, some more 3D scanning, some more CAD work, all the usual suspects. See you next time.